We're still pursuing this idea of finding a solution for f of x equals 0, and we're going to consider yet another method of finding the solution. And this method is called the secant method, and it's actually an approximated form of Newton's method. So let's take a look at an example. Once again, I'm going to draw how it actually works. So let's have the y-axis and the x-axis going like so, and then let's suppose that here is the function that we're trying to solve for. So we're once again looking for this particular point. So what the secant method suggests is that we pick some points. We pick a point x0 and x1, and then we try to connect a secant, so a chord which actually matches those two values. So for example, if I pick x0 to be here, so if I just crudely draw it to roughly this point, and then if I pick, for example, x1 to be somewhere here, so let's have x1 here, right? So we get another point. So then the idea is as follows. You draw a line going through these 2 points. So you draw a line that goes something like this roughly. I'm not being 100% straight here, but this kind of line. And you have the intersection with the x-axis, so that gives you a new value. That gives you x2. And then you project x2 up, and you get a new point, and then you connect x1 and x2, and that might give you a different kind of point, a point much closer to what we're looking for, and that would be x3, and then you would go up, and you would connect these 2 points, and eventually you'll arrive at the result. Now, it may appear to you as though I've doctored this example so that we would always be going from the right towards this point. So let's take a look at a different realization. Let's draw something more tricky. Okay, so let's have another set of axes. I'll move this up a bit. Okay, so let's imagine that our line goes something like this. So it goes from below, and it goes like this. And let's suppose that our initial choices, so our x0 and x1, are actually on either side of the line. So x1 might be here, x0 rather. x0 might be at this particular point, and then x1 might be at this particular point, so somewhere here. Now what happens when you join these two? When you join these 2 points is you get a line that looks like this. So you get a line that looks like this, and essentially x2 would now be here. So x2 would be here, and then you project down to the line, and then once again you connect this line up with x1, and you might get something like this. So you might get a line that goes through here, and you would have the next point, x3, being somewhere here, and you proceed to repeat the result. So actually the iteration formula is very similar to something that we've seen before. In fact, it's the same formula as for the regular fallacy method. So the iteration, the x value at I plus 1 is equal to xi times f of x I minus 1 minus x at I minus 1 f of xi, all divided by f of x I minus 1 minus f of xi. So this simple formula, you just plug in x0 and x1, and you're going to get eventually arrive at a point xn where it's very close to the point that you're actually looking for. So now let's take a look at how to do this in MATLAB. Alright, so here is the implementation of the secant method. It's actually very similar to what we had previously for the other single point iterations, but this time round we have the function we have x0 and x1. Notice the change in terminology. We're no longer talking about a and b. We're not saying that a and b somehow bracket the root. That's not the case. So we have the first two guesses. We have the maximum number of iterations. We specify once again the maximum error that we're okay with. And then we go through the iterations. We calculate the new x value. We calculate the y value at this point, and then we look at the tolerance. And once again, if we're happy with the tolerance, we just break and print the value. If we're not happy, then we recalculate the x0 and x1 positions, essentially reusing the variables. We're not making an array of the x's with like x2, x3, whatever. We just reuse x0 and x1 for the bounds, and we run this again. And when I execute this, you'll see that within 4 iterations, we get within an acceptable tolerance level.